Welcome back. In the previous lecture, we had we were talking about the fixed points and how to use the fixed point results to show existence of solutions to ordinary differential equations. We had seen the existence results for the first order nonlinear ODE. In this lecture, we are going to look at we actually had seen in the previous lecture the first order system of nonlinear ODE, which also includes any kth order nonlinear ODE of some specific form. Today we are going to look at the existence of solutions to, to the second order nonlinear ODE, but the boundary condition is a two-point boundary value problem. So far we have been looking at initial value problem. This is a different situation. This is where so like in an initial value problem, you have an ODE and you are given the value of u at a fixed point. Like if you remember, it was earlier value of u at some x naught or say 0 in this case, then the derivative of u is given at 0. So the value of the function and its derivative is given at one fixed point. That is the initial value problem. Whereas in this case, there is no derivative condition. The value of u is given at two different points. So it's called two-point boundary value problem. You can also prescribe the derivative value. So for a second order, you can prescribe a derivative at two different points and so on. So in this lecture, we are going to look at use again the fixed point results to show existence of solutions to second order ODE of this type, the specific form which we have been considering, where the value of u is given at two different points. In this case, it's the end points of the intervals, which is it's called boundary value problem. Okay, so like previous case, we first observe that if any solution to this problem, first of all, any solution to this problem has to be twice differentiable, right? Because if it has to satisfy this ODE, it has to be twice differentiable. So when we say twice differentiable, we mean it's twice differentiable in 0, 1. So it has to be C2 of 0, 1, right? And here what this notation, this intersection notation means, when you say u belongs to this intersection, you basically mean that u is twice differentiable in the interior and the function can be continuously extended to the endpoints. Okay, so that this boundary condition makes sense, right? So that's what this means. So in this lemma, we are going to show that if you, so this is the minimum requirement to, I mean, for any function to be a solution to this ODE, right? It has to be twice differentiable, and the value of u should be continuously extendable to the boundary, to the endpoints. So whenever u is this belongs to this space and is a solution to this ODE, then u is actually C2 of 0, 1. What we mean here is that it is also twice differentiable at the endpoints. And when we say at the endpoints, we basically mean the one-sided limits, right? So for 0, you take the right, you take the right limit, and for 1, you take the left limit. So under that notion, this function u is also twice differentiable at the endpoints. The reason we are trying to do this is, I mean, the reason, and this is anyway consequence of the fact that if u belongs to this and solves this, then it ought to happen. And this is important from the perspective of fixed point, because for a fixed point theorem, we have to work in a complete Banach space, right? So it's we want the solution to be in C01 and so on. Anyway, so to the proof is just elementary analysis or calculus. So we see that for any x in 0, 1, and if once you fix in x naught in 0, 1, and if you integrate this ODE from the range x naught to x, we get this integral equation here, right? So minus x naught to x, and anyway, this minus symbol is just for convenience purpose, right? I mean, one could have written the ODE without this a priori minus symbol here, but this is for some physical reason to keep track. And during some integration by parts kind of operations, you don't have to keep track of a negative sign if you start with a negative sign here. It's only for convenience purpose. Okay, it doesn't make mathematically or theoretically it doesn't make a big difference. So you have this integral equation. If you integrate in this ODE in the from the range x naught to x, right? Now from your fundamental theorem of calculus, so that equation actually becomes u prime because you're integrating u double prime here, so you actually get u prime x equal to u prime x naught minus this. Okay, so whatever the integral equation is equivalent to this. So from this we from here we observe that we are given that f is a function which is continuous in both its argument. So f is a continuous function on both its argument, where x is coming from 0 1, right, and u, this is in the range of u which is contained in R. So f is continuous in the entire strip here, right? So using that information, and you are just integrating uh, that f here, right? So using the fact that f is continuous in this strip and u is continuous in 0 1, we actually see that, and from this equation we actually can write this u prime of x. You can actually extend the function u prime continuously to 0 1. Okay, from this nice inequality. Now we'll actually show that at the endpoints u prime can be differentiated. So for that, by mean value theorem, you know that if you fix an x, then there is a c between 0 and x such that this happens, right? Ux minus u0, x minus 0, which is x, is u prime of c. This happens for some c. So for every x, there is a c such that this happens. Now you take limit x going to 0 on this side, on this left hand side. So when you take limit x going to 0 on the left hand side, what you get is actually the derivative of u at 0. So this should converge to u prime of 0. Whereas when limit of x going to 0, what happens is as x is going to 0, this choice of c, which depends on x, will also tend to 0. So limit of x going to 0 here, basically on this side actually means limit of c going to 0, right? As x goes to 0, c will also go to 0. So from here we actually get that the u is differentiable at 0, and the u prime of 0 is actually limit of c going to 0 u prime of c, right? So similar argument can be given to show that the u prime of 1 is limit of c going to u prime of 1, like in a similar way, right? For do it for the interval x comma 1 here. So then you get u prime of 1. So basically what we have shown is that u is once differentiable even at the endpoints, right? We have shown the derivative at the endpoints. Now you do the same thing using the ODE, right? We have this ODE here now, right? Use this ODE, use the continuity of f in both the arguments, and using that one can show that u prime use so sorry, this is a typo here. What I want to say is u is c201 or u prime is c01. Okay, so um, this is a typo. Okay, one should not have the double derivative here. Okay, so from the ODE itself, we can show that u is twice differentiable, including the endpoint. So we have established our lemma, whatever we wanted to show here, that if you have a solution to this problem, which is twice differentiable in the interior and continuously extendable to the endpoints, then they are differentiable even at the endpoints. Okay, now this is one way. Now we'll show the other result is what about the solution. So if u is a solution of the ODE, that boundary value problem that we started with, right? If u is twice differentiable in the closed interval 0 1, then u is actually a continuous function in 0, 1 which solves this integral. So basically, right, this integral where this u0, u1 are the initial, the boundary values that we had prescribed, right? u0, u1 are the boundary values. Okay, and this g is usually what's called the Green's function, which is given like this. Okay, this notion of Green's function is something that will come up in second order, even in partial differential equation. When you go second order partial differential equation, basically it relates to if you have come across the notion of fundamental solution and so on. So here the idea of picking up the Green's function comes when where you try to find the solution by locally finding solutions and patch these solutions. That's what this basically means here. Okay, so here you are doing, and so the idea is, if you know the, or more generally for more advanced people, uh, it is this Green's function is usually the fundamental solution or the solution corresponding to the uh, where the source is the Dirac delta function. Okay, and more or less then you convolve with the data for every other data to get, because the Dirac delta function, as we have seen when we did modifiers, is the Dirac delta function is more or less like a approximate identity, right? In this in the space of functions wherever we are working in, so it can be seen as an approximate identity. So more or less finding the solution corresponding to the Dirac delta function, which is the fundamental solution. It's called fundamental because finding that solution is enough to find every other solution in the case, in the most cases, right? So that is how the, so basically it's like localizing the I mean finding a local solution in every in very small neighborhoods and then patching up these solutions, right? So that is how. So for instance, just to explain in our situation, we are given an ODE in 0, 1, right? So what we do is that we choose a point S in 0, 1 and we solve in, say, some epsilon neighborhood of S, right? Basically, we make the source 0 outside the neighborhood and we restrict to the neighborhood and we solve it there locally. So, and similarly, you do in all these epsilon balls of for every choice of S in this interval and so on, and then patch up the solution. That is how, and that's where you will come up with this function, Green's function, which actually convolves uh, with the source term here, right? F is the source term here. Okay. So more or less, you can think of this as a solution corresponding to the identity element, but there is no identity element in this case. So what you have is in the notion of convolution, with the operation of convolution. So you look at the approximate identity, which is the Dirac delta function. So this is a solution corresponding to the Dirac delta function and so on. Anyway, that's you can always see that later outside the thing, just to make you to connect the things I just mentioned these things. So here g is just this function. Okay, it's a two variable function, s and x, and which is given with this way. So then, so what this lemma is saying is that if you, so any solution of the ODE is solution is a solution to this integral. Similarly, any solution to this integral is will actually be a solution to your ODE. Okay, nice. So to prove this, let's start with the first thing. Suppose you use a C2 function in the closed interval 0, 1, which is a solution to the ODE. Okay, then then you start. Let's compute this integral g f, right, where g is given to be as per definition this one. So if you compute this integral using this definition, what we get is in this range 0 to x, we get s1 minus x, which is what we have here, and in the range from x to 1, right? S is from x to 1, in the range x to 1, it is x1 minus x, which is here. Okay, so by just using this definition, we have this. Okay, and we have, and since the ODE is satisfied, we have replaced fs u comma s by using the ODE 10.3. We replaced it by u double prime, right? That is what our ODE was. So now you do integration by parts. Okay, so do integration by parts here, right? Reduce the order of so reduce the derivative order here for u. If you do an integration by parts, things will cancel out, and finally you will be left with this term. You of course have to use this information that u of 0 is u0 and u of 1 is 1, right? When you do integration by parts, you'll get terms, you'll get values of u at 0 and u at 1. So then you will end up with this equation, which is precisely the 10.4 that we have written here. Okay, so we have actually shown this fact that if it's a solution of the ODE, which is C2, then U satisfies this equation, right? Now conversely, suppose U is a continuous function which satisfies 10.4, that is that equation that we had, right? This equation, if U satisfies this, we need to show that U is a solution to the ODE and is C2, right? So from the 10.4, we easily see that U0 is U0 and U1 is U1, right? Sorry. So if I put x equal to 0 here, what you're left with U0, everything else will become 0, right? By definition, so if x equal to 0, you'll put x equal to 0 here, so you'll get x equal to 0 here, which means whenever x is 0, s is also, whenever x is 0 and s is bigger than 1, then you know, so right, when x is 0 here, whenever x is 0 and s is bigger, then this is g0 of s is 0, right? And same thing here, so this will become 0 here, so this entire integral is 0, so what is left with u0? Similarly, when x is 1, you will have u1, everything else will become 0. Okay, so u satisfies the boundary conditions is clear, so we have checked the boundary condition. What we need to now check is that it satisfies the ODE, right? So what we do is that in the we differentiate the given 10.4, the equation. When we differentiate, we have u prime of x, and we will left with u0, u1, right? Because those were first order, I mean first degree polynomials, and so they will have u0, u1. And then when you differentiate that integral, you are going to end up with this, where we have used the definition of g here. Okay. Okay. Now you differentiate once more, then you end up with this equation, which is precisely the ODE that we will get. Okay, so it's a simple thing to check that whenever it's a solution to the ODE, this equation that we 10.4 was satisfied. Okay, this 10.4 is satisfied, and similarly, whenever this is satisfied, uh, then then it's a solution of the ODE, right? And this fact that is C201 comes from the previous lemma, right? In the previous lemma, we had already shown that it's C2 whenever it's C01 intersection, right? This, this lemma, right? From this condition, from this condition, we already have C01, right? So from that, we also get, though we start with C01 here, U is C01 satisfying this, we actually get C201, because once we show that it satisfies the ODE, then it is C201. Okay. Now we will show that whenever the data f is continuous in both the arguments, and it's the Lipschitz function such that this alpha is less than 8, right? It's a positive constant, but the alpha is less than 8, So it's a Lipschitz with this alpha being less than 8. And then for any arbitrary given constants u0, u1, you have a unique solution to 10.3. Right. So far we have said if there is a solution, how does it look like, and so on. That previous lemma were like that, right? So now in this, now we have now we are showing that ODE, so the 2-point boundary value problem that we started with 10.3 actually has a unique solution in this space, right? Unique solution in this space, given the fact that the data is Lipschitz continuous. That is alpha is less than 8. You will see in the proof how this less than 8 naturally appears. So since C01 is a Banach space, right? When given the uniform norm, it's a complete metric space. It's naturally a complete norm space. So then we define this operator T from C01 to C01 corresponding as the RHS of 10.4, right? That interval that we have. So we define this, whatever you do see here in the RHS here, this is our T of U, right? So T of U, so U is here. So we something similar to what we did in the previous lecture, right? We defined an map, right? And then we obtain the solution as a fixed point of that map. We are going to do the same thing here. We are going to define a map, but TU is defined as this one. So you have a U, and which means that any fixed point of that T will be a solution because TU is equal to U, right? So that's a fixed point. So TU is this, right? RHS. So we define T as the RHS of 10.4 here. Okay. And we claim now that this T is a contraction, right, to use the fixed point result, and hence if it's a contraction, it will admit a unique fixed point, which is the solution that we require, because 10.4 actually tells you that any fixed point of T is a solution. That's what we proved in the previous lemma. Okay, so how do you prove contraction? For that, we are given this fact that this F is Lipschitz here. So first observe that by definition Gx, that Green's function corresponding to the ODE, is a non-negative function for all x and s in the interval 0 and 1. So you start with dv minus dw of x, take the norm of that, right? Now you use the definition of t, right? Most of the other linear terms will get cancelled, right? That 1 degree polynomial term will get cancelled, and the integral you will be left with this, right? Where this term is coming from the TV and this term is coming from TW. Okay. Now you use this fact now because f is a continuous function, where both u is also the image of u being a continuous function on a compact set. The range of both v and w will also be a bounded set or a compact set. So for all s in 0 1, this f, the range of this f is actually in a compact set, so you can actually take the supremum of that, okay? Because f is continuous function, right? So it's a compact set. So this is a finite quantity, so if we take the supremum, what is left is 0 1 gs, that Green's interval over the Green's function. Now by the Lipschitz continuity, um, you know that mod of this is less than alpha of its argument, which is this, right? So it's alpha of supremum over this, right? We have given this f of this. So this is Lipschitz in the second argument. You see Rs in the second argument, it's Lipschitz. So that's what we are using here. The second argument here is Vs. So it's alpha times supremum over S mod V minus S. And this, if you actually use this formula for G that we have here, right? we have the formula for g here, right? You are integrating over this here. If you actually integrate over this here, you will get the um, quadratic function there. This one. So integral of 0 1 of g is this. So this integral is over s variable, you see, right? So you integrate use the definition of g here, integrate over the s variable here, then you will get a function of x here, which is a quadratic in x. Okay. Now what we know is that this function x minus x square, okay, so this x minus x square has the maximum 1 over f, right? You can actually you can use calculus to figure this out, right? You differentiate it, and right, you want to show that this is, so you can if you differentiate it and equate it to 0, you get the point, and so you get the critical points. And if you differentiate once more, look at the sign of the second derivative, then you can conclude what is the maximum and minimum of this function. So you will see x minus x square has a so 1 over 4 is the maximum of this function. So this gives you 1 over 8, which becomes alpha over 8 here. And that's precisely why we wanted alpha less than 8, so that alpha over 8 is less than 1. Okay, because for contraction we want this constant here to be less than 1. So we have this, so which means that t is since alpha is less than 8, t is a contraction, so which means there is a fixed t admits a unique fixed point, and that fixed point is precisely the solution, because we have seen in the previous lemma that anything that satisfies that equation will be a solution to the ODE. Okay, so this is how we have shown the existence for a 2-point boundary value problem as well. So we'll stop here for this lecture. We'll meet in the next lecture. Thank you.